Welcome back. Now we are ready to jump into what I call is real nitty-gritties of the molecular dynamics software code. So we begin first with our generalized framework for molecular dynamic simulation. And if you look at your slide, you can see it kind of summarizes what we have talked about. You have x, y, and z three-dimensional Cartesian coordinates. You have second order differential equation that we looked at earlier for particle j1 to n. And these are system of coupled second order nonlinear differential equation, and we can solve them by discretization in time, which we call spatial discretization given by atom size. And we are looking at total energy E is equal to k plus u, where the kinetic energy half mv square and potential energy is represented by a potential energy function. Particles have mass m1, and then if you look at, they have initial vector r1t at time t, and so you have initial position and velocity. If you look at coupled system of n body problem, no exact solution exists, and that is very important that we cannot do exact solution. That is where we resort to computational methods, and you will see this is an equilibrium computational method, and we are looking at the ergodic hypothesis here. So with that understanding, let us move on. Of course, we have to do computational solution. I want to go a little bit deeper into that. So if you look at Ri, which is a arbitrary vector Ri t0 at time t0 plus delta t, you have the position at time t0 minus delta t, then velocities we are looking at 2r1 t0 at time t0, and then you are looking at acceleration term. So we are looking at the initial position, velocities, and calculating the acceleration. Then how do we obtain acceleration? F is equal to ma, and that is where a is the acceleration. So we need to find the force factor. But in order for us to really understand this trajectories, we have to understand the time step. And time step, we know that we are looking at 10 to the power minus 10 angstrom size atoms and their interaction. So if you look at that kind of micro states, then you have to understand what are the time states in that. So if you look at delta t needs to be small enough to model the vibration of the atomic bonds correctly, and that is where vibrational frequency of some of these atoms is important in this case, because they are vibrating at particular frequency, and if you look at that leads to a wavelength. So if your time step is bigger than the wavelength of that vibrational frequency, then you will not capture the motion of the atom, because the wavelength, your box size is bigger than wavelength. So you have to choose time step in a way that you can also look at the atomic trajectory within that wavelength. So how it is going up and down, and in a sinusoidal harmonic oscillator model. And I am introducing a new term here with the harmonic oscillator. If you remember in last section, we derived equation for simple harmonic motion, and that is the harmonic oscillator, which behaves like a harmonic system. But if you look at your slide, this is a harmonic motion. You can see sinusoidal curve here, but if you take that curve and chop it into the time domain, then you look at the vibrational frequency may be extremely high, in particularly for light atoms like hydrogen. There's a time step is of the order 1 to 5 femtoseconds, which is 10 to the power minus 15 seconds. So then you need almost 1 million integration step to calculate trajectory over 1 nanosecond, which is a significant computational burden. So this is where you want to have big enough time step, but at the same time not lose number one, the clarity about the wavelength of the vibrational frequency, as well as you want to make sure that you are computationally not doing million integration, which you may end up doing anyway. But with today's computer it is possible to do, but earlier it was not possible to do such kind of calculation. So we have come a long way. So now with time step, now let us look at the MD procedure. So it is a very simple idea. Let us put it all together, looking at your slide now. So you have to update the time trajectory. So this is what we do, updating the method. Force calculation, then obtain force from the potential, and then the potential, let us say we take Leonard-Jonesium 12.6, we are connecting all, and let us say initial condition is a crystal where we start with the crystalline solid and then we let it go with the initial velocity and temperature. The reason we are doing initial position as the crystalline structure face center cubic, because there are well defined positions for atom. If we randomly assign and one atom goes right on top of the another, you know from 12.6 potential it will feel a very strong repulsive force, and it may knock down the system because too much energy is generated due to very high repulsion. So, you always start with a well defined lattice structure where we know in the crystalline formulation of the molecular dynamic potential function, the forces are at equilibrium close to 0, and that is where you start with a very relaxed system where there are no internal stresses or forces artificially generated because of the position of the atoms. And that is where now we look at the pairwise interaction on your slide for the calculation of potential energy. So, if you take any arbitrary potential energy function phi with respect to r, which is the position, then the change in the position will change the force, and that is where we are able to now find the force vector and calculate the force on any particle x I at a distance r, and then we can calculate f I, the force on a particular I. Assume pairwise, because we are only looking at interaction of one particle on to the other. With this pairwise interaction, we are able to then calculate forces. Once you take pairwise potential in a particular system which has, let us say, 108 argon atoms which are well defined, and these are, as you know, argon is a ideal gas. Let us say in the solid phase it is a face centered cubic structure which is well defined and observed in the X-ray crystallography. So, we know the initial position, initial structure, we start with that and then let the system evolve with respect to time. So, another major issue here is how do we calculate forces on all these 108 particles, and that is very important, because if we take one particle, I have to go to 107 other particles in the system. But what if I take 2.5 sigma length and create a radial distance, and we know that about 3.4 angstrom is the length for a the distance between the two particles of argon. So, that is the lattice distance between two atoms. So, if I go to let us say 2 sigma, then I am going to about 7 angstrom out, and let us say the box size is 20 angstrom to 20 angstrom, and 20 angstrom x, y and z, all 3 dimensions. It is a cubical box. And so, if I look at 2 particles and if I go to 7 angstrom, I have reduced number of atoms quite a bit that I have to calculate, and those are the neighbors of particular atom. So, we take a radial circle, or let us say sphere, around the central particle, and then look at what are the nearest neighbors, and we keep track of those neighbors and then calculate, and that reduces the computational load quite a bit. And so, that is where that is a bookkeeping matter that we look at on your slide, it is explained. So, in that bookkeeping matter gives us neighbor list, and list can be used in several time steps before updating. Each update is expensive, and that is where it involves n by n squared operation. And so, we are going to start with low temperature solids. So, this is how we will take care of the neighboring list, and then from that we can now calculate all the forces on a particle. Thank you.